All right, thanks. So today I'd like to continue discussing order polytopes for a while. And whoops. Yeah, let's actually leave this here. So remember, we had these order polytopes. And you start with a poset P, which has a minimum and the maximum element. Then you define the order polytope of P as the set of all order preserving maps P to the line segment. X0 hat is equal to 0, 1 hat is equal to 1, and then xi is equal to xj whenever I is less than j in our poset. And the last time we were trying to determine the faces of the order polytope. And so let me now try, and basically we had a correct guess, so let me try to make it precise. So faces of the order polytope. Well, what I want to do is I want to define, I want to make an analogy with graph associahedra. Graph associahedra, we had cubes which were sort of connected subsets, arbitrary connected subsets of graphs. So here I want to say that a P tube is a, well, convex connected non-empty. Convex connected non-empty subset of my poset. So what do I mean by what is convex and what is connected? Here, convex, well, convex means that for all I less than j less than k. So what I want to say is that if I and k belong to my set, then j has to belong to my set. That's convex. If I and k belong to capital I, then j belongs to capital I. That is convex. And connected means, well, means that it's, if you take the Hasse diagram of P and restrict to the vertices of I, you get a connected subgraph. Or in other words, if you restrict the order relation to I, is a connected poset. So this poset, restriction of P to I, has a connected Hasse diagram. All right, so that's the notion of a P tube. And now using this definition, we can actually state a description of faces of the order polytope. Face lattice of the order polytope of P is the poset of, I want to say it, basically what I want to do, I want to take P and I want to partition it into tubes. It's the poset of set partitions of P into tubes, into P tubes. And then, as we remember, there was some extra condition, right? You can't just, there was an example, A, B, C, D, this. Right, then, of course, AC and BZ are tubes, and that is somehow not allowed. That would lead to a contradiction if A is equal to C and B equal to D, then you can't have A less than D and B less than C. So how do I make this precise? What should be the condition on the P tubes in general? Well, for now, I don't even, right now there is no, there is going to be no analog of adjacent, no adjacent tubes here. That's actually important. But yeah, you can take an arbitrary, you don't care if the union of these tubes is a tube, but yeah, how do I forbid such examples today? Okay. All right. Yeah, that's actually a good idea. So is it enough for me to consider only pairs of tubes? Could it be that there's like 3 tubes? Somehow any 2 are okay, but the 3 together form a contradiction. So I take a point in the order polytope. That means that some of these inequalities are going to become equalities. And that gives me a partition of my Poset into these tubes. But then not every partition arises from the order polytope. I'm trying to describe the ones which do arise. For example, this one does not arise because pairs are not enough. A cycle. Okay, interesting. So you're saying I should draw a picture. A, B, C, D, E, F. And then maybe I should do something like this and this and this. Nice. And then if I take this tube and this tube and this tube, bounded. Do you guys see? I still get a contradiction here because A is less than D, B is less than F, but E is less than C. So there should be some sort of that's the quotient Poset is still a Poset. Yeah, and actually, so I'm gonna write it in a slightly different way. So into P tubes and such that the directed graph such that the directed graph, which I'm going to call D graph, the D graph D, let's see, I should name my set partition. Set partition capital T of P, so D sub capital T, which by definition, I'm going to look at all edges. I'm going to draw an arrow from I to J, where I and J are 2 tubes in my set partition. And then there is an I in I and J in J, such that I is less than J in P. Right. So I take all pairs of tubes and I draw an arrow from I to J if sort of I is less than J. And yeah, these should be not equal to each other. Right. Then the condition is that this graph is acyclic. What? Equal to the, I wrote 0 here. Yeah, anyways, it should be, this graph should be acyclic. That's the condition. And then it's sort of easy to see that if you give me any partition that's acyclic, then I can choose the numbers so that you actually get a phase of the, for each such set partition, the corresponding phase is non-empty. And okay, so imagine A, B, C, D, E, F are numbers, right? then A and C belong to the same tube, means that the numbers should be A equals to C, right? And then B should be equal to D. But then because A is less than D, and these are in different tubes, I should have A less than D. Yeah, so I get a cycle which gives a control. All right, any other questions? Yeah, okay, so actually, yeah, I want this graph to be acyclic. Yeah, yeah, this is a single word. Yeah, there's no directed cycles. No directed. All right. So, and then we're going to discuss ordered polytopes a bit later in some of their other aspects, like maybe the volume. But for now, let me switch to, let me now go back to associahedra. I want to define Poset associahedra. And then, so here is, it's going to be defined for any connected Poset. Let P be any connected Poset of size at least 2. Then, so I want to define for graph associahedra, we had the notion of tubings, right? Sort of nested collections of connected subsets. So here is another definition. A P tubing is a collection capital tau, capital T, of P tubes such that, again, two conditions. First condition is that any two sets are either nested or disjoint. Are either nested or disjoint. That's the same condition we had for graph associahedra. The second one for graph associahedra was no adjacent tubes. Here I'm going to use something different. Here the second condition is that this graph is not acyclic. The directed graph d sub t is acyclic. So that's it. That's the definition of a P tubing. And yeah, I guess I should say, yeah, first of all, if you take any single element, that's a tube. Any single element is a tube. Also, the whole Poset is a tube. And you can add those to any tubing or remove them from a tubing, and you still get a tubing. So let me make another definition. So let me say that a P tubing is proper if we have 1 less than the size of I, less than the size of P, for all I for all tubes. Every tube has to be strictly between a singleton and the whole set. All right, then where is that? So here's the theorem. There exists a P minus 2 dimensional polytope, which is denoted the associahedron sub P, whose face lattice is the poset of proper P tubings ordered by reverse inclusion. So that's this polytope is called a Poset associahedron. All right, so maybe I should try an example. Let's say I draw some Poset. Maybe I take this one. Here, notice that for ordered polytopes, we assume that it's bounded. But here, I don't have to assume, just only has to be connected and at least 2 elements. So maybe I should draw some Poset. Maybe this one is fine. 1, 2, 3, 4, 5, 6. So let's play the game again. Maybe somebody just tell me some example of a P-tube this Poset. 5. All right. Well, let's take the only proper tubing. So yeah, let's not take singletons because they are trivially 5, 2. All right. One more. 3, 6. 5, 2, 3, 6. Yeah, let me write them down. 5, 2, 3, 6. 5, 2, 3, 6. Is there any more? Two, 3, 4, 5, 6. Okay. 2, 3, 4, 5, 6. Is there any more? No. No. One, 2, 3, 5, 6. Yeah, has to either contain 4 or be disjoint with. Actually, there is no more, right? And the reason is that, so this, again, is a vertex of the Poset associahedron. And then if you remove any one tube, that's going to be an edge, etc. So yeah, maybe I should try to draw the whole polytope for some. Yeah, I have some example for. For example, if my poset is 1, 2, 3, 4, like this, then the corresponding associahedron is going to have dimension 2, right? And then it's going to look like, yeah, maybe, all right, it's going to be a hexagon. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. So yeah, maybe, yeah, let me start. Maybe this is 2, 3, and 1, 4. What's the next one going to be? 1, 4, and 1, 2, 4. What's the next one? 2, 3, and 2. Yeah, actually, oh well, it has to share. Oh, say again. 2, 3, and 2, 3, 4. Okay, nice. Okay. 2, 1, 2, 1, 4. 2, 1, 3, 4. 2, 3, 4, and 3, 4. Okay. Yeah. Closes down to a hexagon. Yeah, and you can try a three-dimensional example, and actually that's a lot of fun. So yeah, anyways, maybe I should continue the example. So why Poset associahedra? When do I get the usual associahedron? Linear order. Okay, nice. Yeah, so if P is a chain 1, 2, going up to n, then the Poset associahedron is just the usual associahedron. It has to be n plus 1. This becomes n. All right. Yeah, and I guess that's an exercise. I mean, it's sort of similar to graph associahedra, but yeah, for graph associahedra, you have no disjoint tubes. Here, you don't have that condition. So it's slightly different. But yeah, it is the usual associahedron. And 1, 2, 3, and 2, 3. Yeah, that's in there. 1, 2. Oh, okay, interesting. 1, 2, 3. Y is 1, 2, 3, 4, and you want 1, 2, 3, and 2, 3. Y. Okay, right. So every tube has to be convex. So if you have 1, 3, then you have to include 4. This is not convex. All right. So yeah, that's an interesting question. If I take an anti-chain, then it's not going to be a connected Poset. But all right, that's close enough. The actual claim is that if P is you take an anti-chain, and then you assign a minimal element, then the corresponding associahedron is the permutohedron. And why is that? Right. Good. Yeah, it's the same argument that as with graph associahedra. Yeah, 1, 2, 3, 4, 5. Then you draw some. Every tune has to contain 0 hat. Then like this tube in here corresponds to the permutation 4, 4, 3, 1, 3, 1, 5. So maximal tubings are in bijection with permutations and etc. So yeah, again, very nice story. And so let me point out one difference with the graph associahedra, which is that this theorem is a 1 week old. Yeah, I just put out a paper on the archive like 5 days ago, and in particular, we don't know anything about these. Okay, so let me mention things. Yeah, I mean it's kind of weird that I actually came up with them from some different perspective, not just out of nowhere. But anyways, somehow these have been overlooked, even though. Yeah, I wrote this paper. Yeah, 1 week ago. Well, I mean, I was writing this, and polytopes were on my mind, so that's that is related, sort of. Anyways. So, but the key point here is that we, unlike for graph associahedra, which had been studied for like 15 years, here we don't know anything. For example, Well, first of all, let me mention a few things that we do know, but we don't kind of know them well. Anyways, some kind of weird consequences. First weird consequence is that any Poset, well, any maximal Y inclusion P tubing has the size of P minus 2. I mean, because it's a polytope, so every vertex has to be a dimension P minus 2. I guess you can't prove it combinatorially, but it's sort of tricky. You can try. It's a nice combinatorial exercise to try to prove this directly without using the statement that it's a polytope. And the second fact is that such tubings correspond to vertices, but then if you have a vertex and you remove one tube, then you're going to get an edge which connects it to some other tubing. So removing a single, well, yeah, any, let me write it down like this, any well, actually, it turns out that, yeah, for a polytope, it sort of comes out automatically. Yeah, I don't ever in the paper prove this separately. Yeah, and so there's a whole bunch of statements you can get out of the fact that it's a polytope. So, for example, any tubing size 1 less, P minus 3, is contained in exactly 2 tubings. So every edge contains exactly 2 vertices. But yeah, that's proof exercise. And then there is a whole bunch of open problems. What is the H vector or the F vector? What is the yeah. Oh yeah, so this is simple. The dual is simplicial, yeah. Which, by the way, why is it simple? Because every maximal tubing is of size P minus 2. So you can always remove any one of those tubes and you get a simple polytope this way, just in the same way as the, yeah, and one other open problem, which I think, so for graph associahedra, we had an explicit realization. We had as a Minkowski sum of simplices. I don't know what happens for, yeah, I don't have any, so I know these are polytopes, but I don't know how to realize them in, like, with integer coordinates. Yeah, there is a procedure. You can obtain them by stellar subdivisions. There's a technique which I didn't teach here, but yeah, you can. It actually took me quite a while, but yeah, eventually the proof is kind of easy, but takes a while too. Any other questions? Hmm? Yeah, sorry. Oh. All right. So no questions. The next topic is triangulations. of arbitrary polytopes, not just two-dimensional. Okay, and so here is a precise definition of a triangulation. But can somebody give me a precise definition of a triangulation? Does anybody have a guess for what it should? Yeah. Okay, interesting. Okay, so I should be using only the vertices, and then the simplices have to only overlap in the faces. Is that it, or any other conditions? Yeah, the union of simplices has to be the whole polytope. Any other conditions? Yeah, you can have a triangulation that. Wait, say it again. Okay. Well, what do you mean the whole thing? It doesn't give me the interior of the polytope. Right. So I don't want just the boundary. I want the whole. Okay. Actually, there's one more condition that is important, but usually is missed when you try to guess. So let me first define a subdivision. A subdivision of a polytope P is a collection. So I'm talking about polytopal subdivisions. Collection C of smaller polytopes such that so here are the three conditions, and it's slightly different from what you're trying to guess, because so the first condition is that for any polytope Q, all faces of Q belong to C. So rather than trying to make things disjoint, I'm just asking that if you have some polytope, then all the faces should be contained in this collection as well. And then the second condition is that for any two polytopes, so that's the condition that you didn't guess. For any two polytopes, their intersection is a face of both Q and R. And yeah, the third one is, of course, that union of all polytopes is P. So let's try to discuss this a little bit. Maybe, yeah, is there a counterexample for 2? Can you have a subdivision of a polytope into smaller polytopes such that some intersection. Oh, okay, maybe I should define the triangulation. A triangulation of P is a subdivision of P into simplices. So I want each element of C to be a simplex. Yeah. Oh, okay. You can have just right if you. I see. So you're saying, yeah, I could have. So examples that violate 2. You're saying 2 squares, which something like this. So if C consists of 5 squares, 1 big one and 4 small ones, then this violates 2. What if, let's assume that, let's say I have a bunch of top dimensional pieces, as you guessed, such that the interiors don't overlap. Yeah, that's a good question. Let me, and the answer is that sometimes I do it, sometimes I don't. So let me add another condition. So sometimes I'm going to assume condition number 4, which is that the vertices of C are same as the vertices of P. Yeah? Yeah. So I want all lower dimensional faces to be in my sets. In particular, this condition should apply to all lower dimensional faces of all my polytopes. But of course, yeah, when thinking about polytopes, I'm only usually going to think about the top dimensional one. But it usually makes sense to include, yeah? You want a picture that looks like this. Sure. If you agree to be on camera, then. All right. Yeah, so you're saying their interiors are disjoint, but condition 2 is violated, because if you have 2 squares here, then the intersection is not going to be a face of either of them. Yeah, actually, well, yeah, the actual reason is in higher dimensions it gets nasty. Which, by the way, so let's try another example. Maybe I'm assuming the 4th condition, that the vertices, I'm only allowed to use the vertices of my polygon, of my polytope. Then can I violate the 2nd condition without having overlapping interiors polytopes? Okay, yeah, let's say I have a bunch of top dimensional things and their interiors don't overlap and their vertices are the vertices of my polytope. Can this be violated or not? Probably that. Interesting. So you want me to draw two pyramids. And you're saying that I triangulate one pyramid like this. So this pyramid is going to be the union of 2 simplices of 2 tetrahedra in this way. And this pyramid I'm going to triangulate like this. And then I smoosh them together. So I get a non-triangulation of an octahedron. Yeah, that's perfect. That's exactly, I think that's the easiest example that I know of. Yeah, impressive. Right, so this condition is really important because you don't want to deal with, if you imagine some higher dimensional things, maybe they are somehow knotted together in some way. You don't want polytopes coming like this with each other. So you want any intersection of two polytopes to be their common face. At least that's how we study triangulations. And so I'm going to call this condition the no new vertices condition. And yeah, I mean, usually in the paper, you either include this or you don't include this, but in the class, it turns out that sometimes we're going to have to include it and sometimes not. So I decided to just make it sort of an optional condition here. Subdivision with no new vertices. Usually it's just, usually say in this paper, we don't use any new vertices. But sometimes it's useful to use to allow new vertices. All right, so examples of triangulations. And one example we discussed previously is that the cube 0, 1 to the n is triangulated into n factorial simplices, which I'm going to call, so let me, and of course, yeah, so here I'm talking about the top dimensional pieces, and then automatically just include all their faces. So nabla sub w is going to be my simplex and consists of all points such that, all points in the cube such that xw of 1 less than or equal xw of 2, etc. less than or equal xw of n. So w here is a permutation in the sun. Yeah, so why is this a triangulation, or is it not a triangulation? How do you check? And this gives a triangulation. So the first condition you kind of automatically satisfied. What about the third one? Is it easy to see that the union of all? Yes. Why? Okay. Yeah, if I have a point in the cube, then the coordinates are ordered, so that gives me a permutation. Nice. So, and yeah, for the second condition, it's slightly annoying. Right? You have two different permutations. Then you have to intersect such simplices. And yeah, anyways, exercise. Yeah, it's kind of similar to faces of the associahedron or something like this, where you have sort of blocks where things are equal in each block. It's going to be a face of each of those simplices. Yeah, and then yeah, you have to check that these are. It's clearly you never get overlapping interiors of two simplices and stuff like that. So yeah, officially this is an exercise. Check that this is a triangulation. And maybe I'll give another example. Let's say I take the order polytope. So P here is a Poset. Then I take the order polytope of a bounded Poset is triangulated. How do I triangulate the order polytope? Yeah. What do you mean chains? Polytopes which correspond to, say again, correspond to chains in P. Okay, so maybe P is 0 hat, 1 hat, A and B. You're saying there's two chains, 0A1 and 0B1. And what are the corresponding simplices? So, by the way, what's the order polytope of this Poset? Does anybody remember? I can't hear you. Hexagon. Wait, actually. Wait, so what are the inequalities? It's a square. Okay, interesting. Yeah, it's a square because A has to be between 0 and 1, and B has to be between 0 and 1. It's a square. What was the hexagon? What is... No. Well, yeah, I mean, x, this guy is equal to 0, and this guy is equal to 1, so actually we naturally have a two-dimensional. Yeah. Okay, so what's the triangulation here? Oh, interesting. So you want to take all simplices like this, where W respects the order. That's an idea, because if you look at these inequalities, if W respects the order of, yeah, so what does it mean to respect the order? Is triangulated into simplices nabla sub W, where W is what is called a linear extension of P. So what is a linear extension? It just means that I is less than J in P implies that W of I is less than or equal to W of J. So it's a way to label the vertices of my Poset by integers from 1 up to n, so that the order is preserved. And then the claim is that these triangulate the whole order polytope. In particular, the number of such simplices is the number of such linear extensions, and linear extensions are of huge interest in combinatorics. Studied a lot, and in particular, you can study them using volumes of, yeah, I guess I haven't talked about volumes yet, but will soon. So yeah, and again, exercise, check that these two are triangulations. And in particular, yeah, for the square here, the triangulation looks like this. This is W equal to 1, 2, and then this is W equal to 2, 1. So here A is bigger than B, here A is less than B. Yeah? Yeah, what is the order polytope? The order polytope right, it's, well, actually, like 2 days ago. Yeah, it's, or actually, was it in today's lecture? Yeah, let me remind you. So it's the set of points which satisfy x0 hat equals 0, x1 hat equals 1, and xi less than or equal to xj if I less than or equal to j in P. And that's for Poset associahedra. So that, yeah, the order polytope is easy. Yeah, it's given by as a realization. Yeah, I know it's confusing. I gave you so many polytopes, and somehow they're all related. But anyways, I'm out of time, so next time we're going to talk about volumes a little bit, and I'll see you all on Friday. By the way, there's homework, which is due in 1 week from now, in case you didn't get the email.